I have so much power as the host.
All
So,
right, I'm
okay,
recording.
cool. Welcome. We have Jesse, Carson, and Philip. And so, what questions do you guys have for me? Where should we start?
I think the biggest one I have is I'm still working on that problem three from the assignment one, and
Okay.
I'm having issues trying to calculate the midpoint of the 3D chord.
Okay.
Both the geocentric and spherical, I think, is what it wanted.
Did you get good XYZ coordinates for your two endpoints, your two stations?
No, I think that was what I was having trouble with. Let me open up my Excel spreadsheet, but I think that was what I was having trouble with, was trying to get those coordinates established in the first place.
Okay. Well, I have to allow it, don't I? We shouldn't have to allow everything. There you go. Everybody should be able to share their screens now. And I'm not sure if you've started sharing, Carson. I'm not seeing anything. Oh, there you go. What? No, still not seeing anything. Okay, I'm seeing your spreadsheet, Carson. Okay. So what are we looking at here? Looks like you have not yet attempted to calculate your.
Oh yeah, I did earlier, but I deleted it all. I forget why, probably because it was wrong. But
Okay.
you want to use that XYZ, and for the X coordinates, it's something like X equals R cosine
It- hmm. So
psi.
let's do this slowly so I can you're on the right track.
Okay.
So remember we, for these problems, we're not considering height, but you should get used to including a height in with your calculations. So the formula for the x coordinate is what? It'd be x time or x equals r plus h, right? So your radius plus whatever height you have, whether that's positive or negative, above or below the surface of the earth, or the surface of our spherical model, right?
Yeah.
So um, let me take over the screen. I'm going to share. I have a page here with it. So uh, where is that? I'm looking for. There we go. All right. So you guys should be seeing my pad here, and it's not focused very well. But I can zoom in. So there are the formulae for the Cartesian coordinates, right? And I can make those a little easier to read. And this looks familiar to everybody, right? These formulae. Those look familiar.
Yeah.
Okay. They're pretty basic. You have your radius value with the height included, which in the case of this problem, we're using a height of 0, correct? And then we multiply it by the cosine or the sine of psi and lambda, depending on the value we want. So what part of that is hanging you up so I can address specifically?
I think it was just that I was getting the formulas wrong prior because I'm looking at your uh, Z formula, and I think the issue is that I
Mhm.
was using the wrong formula for Z before.
Okay. Do you know what you were using before?
I think I was using R plus H uh, sine sine of psi, then cosine psi.
Okay. So Z, in that lecture, I built those for you, right?
Yeah,
Uh, and so from that demonstration, you see why it's just the sine of the latitude.
yeah, that makes
Yeah.
sense.
Yeah. So do you think with that you would be able to continue, or do you want to walk through it with us?
I think I can continue with that. Yeah, I think that
Okay.
solves my issue.
Okay. Now the going the other way deserves um some discussion. If we have XYZ coordinates, so okay, let's not get ahead of ourselves. You were wondering about calculating the midpoint.
Yes, yes.
Okay. So what would you need to do first in order to calculate the coordinates of the midpoint? You would need to get
The
what?
endpoints.
Yeah, you need the XYZ coordinates of your endpoints. And we know how to do that. We just talked about that. So then how would you get the coordinates of the midpoint?
Basically, just take the uh, coordinates of the endpoints, do some coordinate geometry to find out the length, divide it by two, and then you've got your midpoint essentially.
Essentially, but you can break up that into a simple formula that we all learned in probably seventh grade. Um, so the midpoint, if given x1, y1, z1, and x2, y2, z2, we have a good old midpoint formula from back in the day. So if I wanted to get x of the midpoint, that would be what? It's just x1 plus x2 over 2. It's just the average of the coordinates.
Okay. And then
You
is this the
know,
geocentric
these are
coordinates?
geocentric coordinates. Yes,
Okay.
geocentric coordinates mean um, Earth-centered, Earth-fixed Cartesian coordinates. Now, Cartesian means it's from Descartes, who Rene Descartes created the system of, well, he um, democratized the system of Cartesian coordinates, which is the just the grid axes that are perpendicular to each other. X Y would be a two-dimensional coordinate a Cartesian coordinate? XYZ is a three-dimensional Cartesian coordinate.
Yeah.
So then we have Z1 plus Z, finish what I'm doing here, over 2. So those are Cartesian coordinates, and the system, the reference system we use to refer to those Cartesian coordinates we called Earth-centered, Earth-fixed, or ECEF. They all mean the same thing. Cartesian coordinates, Earth-centered, Earth-fixed, XYZ. So does that clear up that question?
Yeah. Yeah. I think that just about solves that.
Okay, cool. What so once you have the XYZ coordinates of the midpoint, you're then asked to get the latitude, longitude, and height, right?
Yeah. Those would be
Okay.
the spherical coordinates, correct?
Correct. And we have to be careful because similarly to calculating azimuth, for one of those values, we need to consider quadrants. Now, how if longitude, let's say we're considering east longitude, what is the range in which we must represent longitude? What's the range of values that we have to represent longitude if we are in degrees?
0 to 180, right?
0 to 360,
Oh,
right? Unless we decide to, once we get to 180, flip and go from east to west, you know. But in effect, if I am looking down on the Earth, I decided not to monkey around with the tablet board anymore. I just can't draw on it very well. This is much clearer. So here's the pole. We're looking straight down on the Earth. And let's say this is the line that goes through Greenwich, England. What is the longitude of that line?
Zero.
0. And let's say what would be a candidate? Let's just guess what the longitude here would be. East longitude. Let's stay in east longitude. What might that longitude be if you had to just pick a number? What's a realistic number there?
Like 36 degrees or something.
36. Tried to make it more like
Or
45.
yeah, 45, I guess.
Let's call it 45 degrees east longitude. And let's see. If I draw my grid, I can't stress enough how important it is to draw sketches for these to build your sense of concept image. This would be, what would this here be? This one from the pole outward, because remember, we're looking down, there is no north, south, east, west here. What would this one be?
That's just your 90.
90 degrees east longitude. And what would this be here?
Be 180.
180. Okay. And then this would be what?
270.
270. Okay. So let's consider longitude. What is the formula that we learned for establishing the longitude from a set of XYZ coordinates? And by the way, this is X. This coincides with the X axis. This coincides with the Y axis, right? What is the formula that we came up to discover longitude from XYZ coordinates? Longitude is some point. Let's put point P, say here. Here's point P on the surface of the Earth. It has an XYZ value. What would if we're looking down on the Earth, we're thinking of this like it's in 2 dimensions. What would the value of this, let's see, this is P. What would the value of this dashed line be? In Cartesian coordinates?
Wouldn't that be the z-axis?
Nope, we're looking straight down. The z-axis is coming straight out at us from the pole. We have an x-axis and a y-axis because we're looking straight down on the Earth. So this would be the top view.
Okay, then that would be on the y-axis,
So
technically,
this,
right?
yeah, this would be the y value of P, right? If the Cartesian coordinate, if I say P is at X P, Y P, Z P, we can't see the Z value because we're looking top down. So in this coordinate, YP would be this distance here. Make sense?
Yeah.
Just like the old 8th grade math, we're looking at X and Y coordinate systems. That's the Y value. What would this be?
That's just your x coordinate, x
Yeah,
of p.
that's the X of P. How would I represent Z of P?
In this drawing, you can't because
Yeah,
it
I really,
goes out.
yep, yep. The Z value would be the axis along this axis here down to the equator, right? The distance, the Z value would be the distance from point P straight down, projected down to the equator, to the plane of the equator. But the plane of the equator is, we can't, we're looking top down. So we can't really draw the Z. So we have X and P. And what was the formula that we learned for the longitude, getting the longitude? What we're trying to get is this angle here, right? That's our longitude of P.
We can just take the inverse tangent of the coordinates then.
Yep, let's construct it. So the tangent of the longitude of P would be equal to what? Tangent, remember old SOHCAHTOA. What's the TOA?
Opposite over adjacent.
Yep, so it would be what?
Y sub P over X sub P.
Yep. Exactly. So if I wanted to know the longitude of P, I'd take the arctangent of both sides, right?
Uh-huh.
And what do we know about the arctangent function? What range of values is the arctangent function going to return always in terms of degrees?
0 to 360.
0 to 90.
Oh, okay.
Yep. It's all the arctangent will always return the angle from 0 to 90, right? Now, if I were to, just as an aside, with azimuth, we do as equals the arctan of the departure over the latitude, so the difference in the eastings over the different distance in the northings. Well, if I'm looking at the north, this is just sort of a review of how this works. What angle is the arctan returning?
Uh, 0 to
Northeast.
90.
It is, but remember, it's returning this value off the north axis because we put the horizontal value, the horizontal delta in the numerator. We kind of flipped it. Now, if we were to take the northings over the eastings, it would return this angle. It's really important when you're trying to walk through these azimuths. So in this case, we are taking the Y value over the X value. So since I demonstrated that we have the Y value, let's just consider this here. If I'm taking the tangent, that would be the Y value over the X value. If I take the arctangent, undo it, what's it going to give me? It's going to give me this angle off of the X axis. It's a little bit different than azimuth because in azimuth, we're concerned with the value off of the north axis. That's why we do the eastings over the northings. So it will return this angle. But remember, longitude we measure from the 0 degree Greenwich, England, or Greenwich line, and it increases as it goes eastward. So in this case, the tangent function is always going to return the angle as it relates to the x-axis. In this case, it will return a positive lambda, right? Because it's positive as we go counterclockwise. We're working with east longitude, which means that our dial is going counterclockwise. We're measure everything to the east or east longitude off of this x-axis. So if we're in this quadrant, we'll call it quadrant 1, what would I add to the value since the arctangent function is always going to return a 90-degree, something between 0 and 90. It's going to return it in relationship to the x-axis. What would we add to this value? What would our adjustment constant be to get this longitude? Because remember, we always have to, since we are concerned with 0 to 360, we have to somehow take a value that's always in between 0 and 90 to what we need, right? Over here in quadrant 1, our longitude is going to be from 0 degrees to 90 degrees. Over here, now since we're constructing our Cartesian system in this manner, and we're going counterclockwise, as opposed to azimuth, we're going clockwise off the north axis. If you draw that a few times, it's going to make total sense. So in quadrant 2, what would my longitude be here? Somewhere between what?
90 to 180.
90 to 180. Hopefully, what you guys are really picking up is the fact that the world of plug and chug is behind us. We have to analyze situations to figure out how to extract the value that we need and then check that that value makes sense. So down here, this would be our quadrant 3. What would the possible values be there?
Just simply 180 to 270.
180 to 270? Yep. And in quadrant 4,
270 to 360 or 0 because they are technically the same.
yep. Yeah, exactly. Now you'll note in our learning about calculating azimuth, we number our quadrants differently, don't we? We have quadrant 1, quadrant 2, quadrant 3, quadrant 4. Because when we're calculating azimuth, we're interested in the angle off of the north axis. So we're interested in a clockwise direction. Right? Sure. I mean, it makes sense. Azimuth is defined as being the angle clockwise from the north axis. East longitude is defined as being the angle counterclockwise from the x-axis, the positive x-axis. So in this case, this is going to return some value. The arctangent function always returns the way we have it set up, this angle here, and it's going to always, the arctangent function is always going to return a value between what?
0 and 90.
0 and 90. So what would our C value be here, our constant, our correction constant for quadrant?
And that one, just 0.
0.
Okay.
Okay. Now, what if my P were over here? Well, let me get a different color. I don't know what happened to my green. I need a green. I'll use red. Let's say over here I have P. P2, or I'll call it Q. This is point Q. Okay. I have my, if I were to impose the Cartesian coordinates, colored pens are awesome. You guys should definitely invest in a set of colored pens. They really help. All right. So what is the distance? What is this value? What's the length of that dashed line going vertically?
That'd be y sub q.
Y sub q. And likewise, what would the dash value be here?
X sub q.
X sub q. What angle is going to be returned if I put this y and x value in?
Be a 90 degree angle.
It'd be a value between 0 and 90
Yeah.
because we take the tangent. And just like I drew this here, it's going to return this angle over here. What's it going to return over here?
It'll return the angle from xq over to the other line.
Yep. It's going to return that value. That's the way arctangent function works. It's always returning an angle off of the axis that we've put in the denominator here. Okay. And is the angle that it returns going to be positive or negative? Remember, in our longitudinal graticule system, counterclockwise is positive. So what is the positive or negative value of the angle it's going to return is?
It's going to be negative.
It's going to be negative. So what do you think, what do we need to add in order to get the longitude that we need? So this is going to return that value. What do we want? We want that, right? Longitude is defined. East longitude is defined as the counterclockwise angle off of the positive x-axis, but we have this angle and it's negative. So what do we need to add? What would our C value be in this case that we're going to add to our equation, add to get the value?
You would just add 90, right? Oh
What would
no,
happen?
you would subtract 180.
Subtract,
Add.
add.
Hold on. Yep, add 180.
Yep. And what if we had another one here? Let's say R. Arctangent function is super useful, but you really have to think about what you're getting. So here, what would this value be? The dashed line I just drew,
Y sub r.
y sub r. And what would the dashed line up here be?
X sub r.
X sub r. And what angle is it going to, what angle is the arctangent function going to return?
It's going to give you that lambda r angle.
Uh, Just like I drew these here. Where would I draw that over here?
For that lambda r, that would be going from the x-axis down into, yeah, it'd be going counterclockwise this time.
Yep. So it'd be what? This is really a misnomer. This isn't our lambda. This is the arctan function. This is actually our lambda up here. That's a little bit confusing. I shouldn't call that lambda. This is just the arctan function. This is our tan inverse of Q. So this would be our arctan of that. So what would I add to this value to get my longitude, my east longitude? Because is this going to be positive or negative?
That'll be negative, so you have to add the 270
Why would it be negative?
because we're on the west.
Think about it in terms of clockwise and counterclockwise. We said that counterclockwise is positive. That's how we got a negative arctan here, right? So what value would my arctangent be, positive or negative here? That's
Oh,
returned?
wait. I guess if you look at it in typical quadrant formation, because that x would be negative and the y would be negative, so it would be a positive,
It would
right?
be a positive, right?
Yeah, because
In
negative
fact-
over negative.
What's really interesting is here we have a negative x, negative y. Well, look at this. The negatives cancel out. So the arctan function doesn't know which side of this thing you're on. So it's going to return a positive value here. So what would my C value here need to be in order to get this whole angular value?
Well, in that case, it should be 180, right?
180. This should be really familiar. This is exactly how we form our correction constant when we're determining azimuths. We've just flipped, right? It's just kind of flipped because with azimuth, we add 180 if it's in the southern hemisphere. Here, we're concerned about east and west hemisphere. So what about over here? What would I add?
For that one, it would be 270.
Let's look at it. So let's make this an S. Call this point. I'm going to put this on the surface here. Point S. Oop, that should be solid. Okay. This is my what? The dashed line is
Y sub S.
Y sub S. And if I were to do a dashed line up here, that would be what?
Y, yeah,
What would this distance be? From the pole to here,
X sub S.
X sub S. And if I take the arctan function, what is it going to return? Where am I going to draw the angle that it returns?
from x sub s to that lower line.
Yep. And what direction is that?
Clockwise.
So is that going to return a positive angle or a negative angle?
Negative.
Negative. So what would I add in order to get, since it's returning this in the negative, and I want this all the way around to it, what would I add to that arctan to get my longitude?
What is that 270, right?
No, if I add 270,
Put
not
in
gonna
the
give you
first
anything.
quadrant.
yeah,
90.
nope. If I want the angle all the way around from the x-axis, and what I have is this negative angle, I would need to go all the way around and then add this negative, right? All the way around is what value?
That would make it
360.
360.
360. Yep, C equals 360. Because if I add 360, or if I add a negative arctangent, a negative angle to 360, it's going to make it less, right? It's going to make it the complement of the 360, which is the longitude here. Let's try it out.
Yeah, when you said it like that, that makes sense. It's
Yeah. Yeah. So these drawings are really, really, really helpful. So
mhm.
is anybody confused by that adding 360?
No, I think I get that.
Okay. Jesse, are you all right with it?
Yeah, that makes honestly when you said the compliment and everything, that makes perfect
Okay.
sense when you said it like that. So
Cool.
yeah.
Philip, you're good?
Yep, I'm right there with him.
All right, cool. So when you're calculating the longitude, keep that in mind. You want to be thinking, okay, where is my XYZ? Well, I'm getting a little cluttered here, but over here, my in terms of positives and negatives, let's see, I'll use this. So point P here, so X sub P and Y sub P here, would X be positive or negative?
Be positive.
Positive. How about Y?
Also positive.
Also positive. And this, by the way, this is how you learned trigonometry. This is how you learned the mathematical rotational coordinate system. Because in mathematics, we're always going counterclockwise off the x-axis. Every math class you've ever had has done it that way. We just make it weird when we get into surveying and start talking about azimuth. Azimuth is an outlier. It's a black sheep. But this is exactly how you learned mathematically working with circular coordinates, polar coordinates. So over here, x sub q and y sub q, in terms of positive and negative, what would x sub q be?
Negative.
Negative. And what would y be?
Why would be positive?
Be positive.
Y is positive. Just think of the regular generic old XY axis. That's what this is. This is pure polar coordinates. How about down here? X sub r and y sub r. Positive or negative? X sub r, positive or negative?
They're both negative.
They're both negative. And x sub s and y sub s. What would x sub s be over here?
The x is positive, but the y is negative.
Correct. So when you're looking at your Cartesian coordinate system, something should be, a rule should start forming in your head now. If x is positive and y is positive, our C value is 0. If x is negative and y is positive, our C value is 180. In this quadrant, if they're both negative, our C value is 180. And over here, if x is positive and y is negative, our C value is 360. Now, 360, Philip said earlier, 360 is the same as 0, right? What we could do to simplify the rule that we're making is we can just look at the x value. We can say if x is positive, let's add 360. If we get a value greater than 360, let's just take 360 out. Right? Because polar coordinates are cyclical. Doesn't that make sense? If the x value is positive, why don't I just add 360? And if I end up with a value that is 470 degrees, well, I know if I subtract 360, it's going to be the same thing, right? Does that make sense?
Yeah.
Yeah. This is just a way, that's called the mod function. It's just a way of simplifying these 4 cases down to only 2 cases. What if the x value is negative? Well, doesn't matter what the y value is. In both cases, I'm adding 180. C is positive 180 in both scenarios. So what we've done is we've taken these 4 rules and reduced them to 2 based on just the x value. If x is positive, add 360. And then mod out 360 if necessary. If x is negative, just add 180 and be done with it. Make sense?
Yeah, I think so.
Okay. If you play with it, that'll be clearer, but certainly you're welcome to work with the 4 rules. The rules of x and y in terms of positive and negative to get your constant, your correction constant. Now, is that pretty good on that? You guys feel good about that?
Oh yeah, I got crazy good notes on that.
Good, good. And then this video is going to be posted, so, you know. Okay, so now I'm going to mess with your brains a little bit. What about latitude? I need to put something. Now with latitude, instead of that top-down view, we're going to look at a lateral view, or as though we're standing on the plane of the equator. Isn't this better than looking at my stupid drawings on that digital tablet? Ah, that thing's horrible. I suffer with that.
You just got to get the right application. I mean, I do everything on an iPad and just
Yeah,
use an app called Notability, and the thing is awesome.
that's way too advanced for me. I don't want to work that hard at software. I like pencil and paper. I'm old school like that. Okay. So if we're looking at the lateral view of the sphere we're calling the Earth, we're using a spherical model. How would I label this just right off the bat? This would be what would this point be?
That's the Z, right?
That's the pole,
Or the pole. Yeah.
but you're way ahead of me there. This is which axis?
It is the Z axis.
The axis, right? And what would the horizontal axis be?
That's our Y.
Well, it's X and Y.
Or
What happens
yeah,
when what happens when we have perpendicular axes? It's a plane, right? And what is this plane? Starts with an E, ends with quater.
Equator.
Yep.
Yeah.
And we just note that that's a plane. Okay. So what is the formula that we derived for latitude, for getting latitude from the XYZ coordinates? Let's say let's do this like we did before. Let's say we have some point P. I'm just going to put it I'll put it here on the surface of the Earth, P. And here's my vector going from the center to point P. Okay. And I just do like I did before. Again, just kind of building up our polar coordinate conversions, just like we learned in vector calc. What would this be? What would the distance of this, what would the length of this dashed line be?
It'd be a Y sub P? No. Or Z?
Z sub P.
Yeah. Yes.
Now this is the tricky one. What's the length of this here? Remember, this exists on the XY plane. It's not necessarily along the x-axis or the y-axis.
That'd be R sub P.
Nope. This is actually R sub P here. If I were to take this and flip, so I was looking down at the pole, it would kind of be like this. I'm just doing a little diagram as though we were doing a top view here. And here's my point P. And this dash line here would be the dash line from the z-axis or the spin axis out to the point, right? But since we're looking down like we were before, when we have a top view, our axes are what? X and Y, right? So looking at the little diagram here, what would these axes be? Looking top down.
Those would be our X and Y.
These would be our X and Y. So what would the length of this be? This is my Y value here. This is my X value here. What would the length of this line be?
Oh, that would be the oh gosh.
Good old distance formula.
Yeah.
Starts with square root. Ends in x squared plus y squared. Right? I'll write that out here better. That's just the distance formula, isn't it? If I have a right triangle, say I have a right triangle, this is a right triangle, isn't it?
It's just Pythagorean's theorem for
It's just,
finding the
yeah,
distance.
yeah. It's just the Pythagorean theorem. If this is 3 and this is 4, what would this length be? The old 3, 4, 5.
5.
Yeah, 5.
Yeah. That's because the square root of 3 squared plus 4 squared equals, well, what? 9 and 16, 25 equals square root of 25. Oh, that equals plus or minus 5. That's just, your brains are tired. You should be able to do this without even like, you should be able to do this while you're chewing gum and walking. So that makes the length of this line right here. Remember, now I'm going to flip it back. So I'm looking laterally at the equator. This is the square root of x squared plus y squared. Now, what angle am I interested in getting the latitude? The latitude is up here, right? Right? How do we define the latitude?
You're drawing it slightly out of frame, by the way.
Oh, sorry. I'm going to segue it just a second here and say that we do ourselves a disservice by associating latitude with the small circles on the globe. Really, what latitude is defined as, then this is what we've been doing since the beginning of the term. Latitude is this angle, isn't it? That's the definition of latitude. It's the angle off the equator. That's why this is 0 degrees latitude. What is the pole? What latitude does the pole lie at?
Zero.
Nope, the equator is 0.
Oh yeah, that's right.
Isn't this a right angle? You gonna make me give it to you? If this is the angle of the latitude up to our point P, what is the angle of the latitude to there?
That
90
goes
degrees.
to a 90.
90 degrees. The pole is at 90 degrees latitude. And if you look at a globe or a representation of the globe, it will say the pole is at 90 degrees. So how do we get this angle?
Oh, that's your psi minus nine or 90 minus psi, right?
Nope, that's this angle.
Or oh,
If I have a value here, because remember, we're starting with known Cartesian coordinates. And if I have this value here, and I have this value here,
oh, it
how do
would
I get
just
this angle?
be the inverse tan of the z sub p over your square root x squared
Yeah.
plus y squared.
Yeah. If I call this psi, then good old SOHCAHTOA, the tangent of psi equals opposite over adjacent right? I take the inverse tangent of both sides and I get arctan. I had a brain fart for a second. I went on vacation. Of z sub p over x squared plus y squared. There we go.
Are those x and y sub p's or are they just x and y?
Well, in the case where we're talking about a specific point, they would be sub p. I'm just giving the general formula. So in this case, yeah, I should have p's. Good call. I know that's hard to read. It's a little out of focus, but can't do much about it. It's a little better. So you can construct all three of these formulae on your own. And by the way, what would I add as a constant on this side? A correction. What would I add?
Zero.
Yep. Now here's the, let's say my point's over here. Point Q. Without making any X's or Y's or anything, what is the arctan function, the way we constructed over here? If I were to construct it for Q, what angle is the arctan function going to return?
It'll give you a negative.
It will?
Oh, no, it won't. Not in this case because we're fully above the equator. Okay. Yep.
It's kind of weird.
My brain was on the other axis.
Let's see. Would it though? Would it though? Would it though? Wait. I don't want to lead you astray. Let me think about this.
That's still technically the negative x axis, right?
It is, but we don't have X's and Y's. I mean, we do, but we're taking the square root, which is always going to give us a plus minus. The only thing you need to know is it's going to return this angle. And we call that north latitude. So here, C would be what? Isn't this already returning the angle we want?
Right, from the 180 degrees.
Uh-huh.
180 minus psi gives you that angle.
This is the nuance of the graticule system. It's already giving you the angle you want. Isn't this the definition of latitude, the angle off of the equatorial plane? So yeah, it's returning a negative angle, but if we were to add or subtract something from it, it would give us something out here. We want this angle. That's why the square root returns positive and negative, because it could be this angle is positive over here, negative over here, but we only care if it's north or south. Now, think about this. What is the range of possible values for the latitude? Whether it's north or south.
That would have to be within the 180 to 90, right?
Nope. The equator's at 0.
Oh, because it's 0 to 90 on both
Yep.
quadrants.
Yep. Latitudes, we don't care about quadrants. They're just hemispheres. That's why
Yeah,
I was going to mess with your brain a bit.
you can treat this more as like going northings and eastings, right? Versus azimuths.
Nope, not even that. Think of it. It would be most analogous with bearings.
Yeah. Yeah, right.
Yeah.
North
Yeah, not azimuth.
37 degrees, 30 minutes east, right?
Yeah, because that's always returning the angle off of the. So bearings are what we get when we don't adjust for quadrant to get the azimuth. It returns a bearing. The arctan function, the way we set it up with the eastings over northing, the delta eastings over delta northings, returns a bearing. And then you just apply the quadrant you want. So yeah, it's analogous here. If we're in the southern hemisphere, our C also equals 0. C equals 0. We don't have to adjust for quadrant in any of these. We just have to know if we are in this north hemisphere or the south hemisphere. That's it. Latitudes are actually easier. So for longitudes, we have to adjust for quadrant, knowing that we're going counterclockwise, in which ways, that's a positive direction. For latitudes, since latitudes are more like bearings. That was a good call, Philip. Latitudes are more analogous to bearings. We only care if we're in the north or south half. We have, whatever, for 30 degrees north here. Well, it's also 30 degrees north over here. Or I guess that would be more like 65. Down here, if I have a point, my arctan function is going to return this. I don't care if it's positive or negative. I just know that that's what? 37 degrees south latitude. Same
Yeah,
over
and
here.
from there, it's just depending on whether it's the easting or westing.
Hmm. Well, no. Northings and eastings don't try not to think about northings and eastings. Northings and eastings are, if you're going to think of that in terms of just an analogy to try to bridge that gap of understanding, that's fine. But we have not even talked about northings and eastings. Northings and eastings and elevation, we're going to talk about that later in the term. But that's a completely different reference system called ENU, and it's a completely different animal than what we've been talking about.
Okay. Yes.
Analogy wise, here we're just talking about X, Y, Z's and latitudes and longitudes and heights.
When, yeah, what I mean when I refer to northings and eastings is bearing. So I get what you're saying
Yes.
though, because that
Yeah.
could be
Yeah.
confusing. A
Right.
northeasterly bearing or a
Right.
northwesterly bearing. That's what I'm referring to.
Right. Yep. But latitudes are even easier because we don't care which side of the Z line it's on. It's always going to be uh south latitude or north latitude. You never hear of a northeast latitude. That's what the longitude does. Remember, we're working in 3D coordinates here, so it just kind of tweaks your brain a little bit, but it's all analogous. Yes. So I wanted to hit that pretty hard because um, it's important when you are considering latitudes and longitudes to know that I don't have time in lecture to dig into it that deeply, but I am going to post this so that everybody has the advantage of looking at this. Um, it's really important as we go through these lectures. These lectures are super compact, super dense, and a lot of this kind of work you've got to do on your own. You have to really suss out what's going on. All right, cool. Um, I think I've fried your brains enough. Do you have what other questions might you guys have? I kind of went on a tangent there, but tangent. Um, I intended to do this tonight, so it's like a free lecture.
This going over the latitude stuff, I understand that a whole lot better because that's how I feel when I'm actually working because I'm dealing in bearings versus
Mhm.
azimuths,
Right.
and I'm dealing on the surface of the Earth, which is like how the latitudinal stuff relates.
Yes. Yeah. So as surveyors, we're used to working with bearings. We don't work with azimuths. I mean, cartographers work with azimuths quite a bit. Um, in navigation, we work with azimuths sometimes, like in seagoing navigation, that kind of thing. A lot of times we work with azimuths. But it's just a convention, you know.
Unless you find it in a legal description, and that drives me nuts.
Then you have to do the conversion so you can think about it.
Yeah, it's
Yeah.
horrible.
Yeah. Uh, I have not seen an azimuth in legal descriptions myself, but I'm sure there's certain parts that, it could be Hawaii. Well, Hawaii uses, I think Hawaii might use azimuths off the south axis.
Yeah, I don't understand why you would use it, but I've also seen northing and easting coordinates in a legal description, which
Yeah,
is frustrating.
yeah, that's I think what that was somebody showing off. I've seen it too, and I think it's terrible. It's a horrible practice. Um, legal descriptions are not for the surveying world, they're for the legal world. And the legal world doesn't care about northings and eastings or anything like that. It's too much math. Lawyers and judges can't do math.
True dat. Neither can civil engineers.
Except in patent law. Yeah, true that too. So yeah, we love to rag on civil engineers, don't we?
Yeah, they are the worst.
Yeah. If you like plug and chug, go to civil engineering. So, all right. Any other questions for me?
I think that's all I've got now, personally.
Yeah,
Okay.
no, I'm good here as well.
Cool. Well, this was a good one tonight. I like
Yep.
these productive sessions.
Yeah, it was. Thanks for explaining the longitudinal stuff because that was tripping me up, but it makes a whole lot more sense now.
Yeah. As we go forward, you guys should be doing a lot of drawing of these pictures. You know, get yourself a drafting compass and straight edge and different colored pens and really think about definitions and how that plays out because it's going to get increasingly more important, especially as we start getting into ellipsoids. You know, the spherical stuff is easy. It gets a lot more interesting when we get into ellipsoids. So, with that, Carson, thank you for recording this. And if you would do me a favor, and I'm not sure what you do at this point, Eric Lundeen recorded the last Zoom session. You might reach out to him and find out what you need to do to get it. What he did was he emailed me a link, and then I posted the link to Canvas. So my guess is that you're gonna have to do the same thing somehow, but I don't know how that works.
Okay, I'll figure out something.
Yeah, I appreciate it.
Yeah, no problem.
Yep. Yeah, I've tried recording straight to my external hard drive